last time we started the degree of kinematic indeterminacy, so we're going to continue a little bit on this, and hopefully we will finish soon and start a new topic. So I extended the homework until I believe next week.
Yep, Tuesday.
Okay, so you should have more time until you finish reviewing this topic. I want to tell you something. If you have any questions, try to send me a message on campus. Emails, like you can, but the thing is sometimes I get mixed with a lot of emails, so I might miss your emails. So try to send a message on Canvas, so when I go check Canvas, check the questions, answer them, and just to make sure that your email doesn't get like mixed up in other emails. All right. Okay, so you guys, if you remember from last time, we started talking about the degree of kinematic indeterminacy, which is a little bit completely different from the degree of static indeterminacy. In static indeterminacy, we are looking for the redundant forces that the structure doesn't need to be stable. Kinematic indeterminacy is kind of like we are looking for the degrees of freedom that the structure has. And we had a bunch of rules, and we called this IK. And we had one for the plane truss, one for space truss, plane frame, space frame, and number 5 for grids. Okay, if you guys remember, each joint, if it's in the plane, has 2 degrees of freedom for the truss, and the reactions is the one that stop the degrees of freedom or restrain the degrees of freedom. So the IK for the plane truss is 2 multiplied by joints minus the reactions. IK for space truss, each joint has 3 degrees of freedom minus the reactions. And the plane frame, IK is equal to 3 multiplied by joints, because each joint had 2 translation and 1 rotation, minus or plus S if you have the intermediate hinge, because add more degrees of freedom, minus reaction. Space frame, IK is equal to 6 multiplied by joint plus S minus the reaction. Grid is a little bit tricky. I know last time I put that IK, if you guys remember, do you remember the grid last time? I put it 3 joint plus S minus reactions. The tricky part is the S. Before we said, do you guys remember the rule for S? It's n minus 1. The number of members connected to the intermediate hinge minus 1, right? So this intermediate hinge before only had one moment when we talk about frame. Because if you have a frame like this, so this frame we say, oh, the moment around this hinge from the left or the right or for the whole structure is going to be 0. But for grid, there is 2 moments. There is rotation, there is torsion, and there is moment, there's 2. So, but the thing is, it only happens if you have spherical or cylindrical hinge. What? When that happens? When you have 2, like if you have spherical, something like this, the moment is equal to 0, and the torsion is equal to 0. Like if you have a member like this, and there's a ball hinge at the end, so the moment is equal to 0 because it allowed the rotation, and the torsion is equal to 0 because it allowed the rotation that way. So 2 moments are equal to 0. So if I told you that this is a cylindrical hinge, so this rule still applies, n minus 1. But if I told you this is spherical hinge, so each member has the moment is equal to 0 and the torsion is equal to 0, so that provides 2 equations, and that provides 2 equations. So this rule is going to be equal to S, let's say, is equal n minus 1 if it's cylindrical hinge. is equal to 2 multiplied by n minus 1 if it's spherical hinge. Alright? Why is 2? Because in the cylindrical hinge we has moment and torsion, 2 moments. Okay? Alright, so that is the rules that we have. So let's solve. I'm gonna put some examples over there and let's try to determine the degrees of freedom. Okay, I'm gonna put Alright, so let's solve these examples and let's try to find the degrees of freedom. And we need to make a rule when we count the number of degrees of freedom. This is the order that we do them. Like if I have a structural member, something like this. Are you guys studying this thing? Okay, thank you. Alright, so if I have a member like this, we count the degrees of freedom that way. The first degree of freedom, like this is a free member, like something like this in the air, that's a free member, has degrees of freedom at the end and the other end. So we count the points from the left, and X is degree of freedom number 1, Y is degree of freedom number 2, and the rotation counterclockwise is degree of freedom number 3. That is how we count the degrees of freedom. Then you go to the other point and you make, this is number 4, this is number 5, this is number 6. So 1, 2, 1 is X, 2 is Y, rotation is 3, and it's counterclockwise. Same thing, you will go to the other one. This is how the order of the degrees of freedom, how we count them. So without applying in these rules, can we try to find the degrees of freedom in these structures? What is the degree of freedom in the first structure? How many degrees of freedom do I have here? 0, right? Because the end is fixed and the end is fixed, so there's no degrees of freedom here, 0. How about here? 1, what is it?
The rotation.
Rotation. By the way, when we say degrees of freedom, we say translation, rotation. We don't say moment. Yeah, it's kind of almost the same thing, but moment is kind of reaction. Okay? So let's say there is a translation or there is a rotation degrees of freedom. Okay? So, alright, so I'm gonna write it counterclockwise, and it's only 1 degree of freedom. How about this one? 2, which is rotation and translation, but I'm gonna put 1 on the translation and then 2 on the rotation. How about this one? 2, how it's look like? The up 1, so this is 1 and this is 2. This one, a little bit tricky, but we talked about last time. We said if there is a spring, it's basically, it doesn't restrain the degrees of freedom. It's still, this point can expand X and Y because the spring is compressible. So the degrees of freedom here, there is 1, 2, and 3. So basically, if you saw a spring in a structure and I told you try to find the degrees of freedom, try to imagine that this spring is not there because it doesn't restrain the degrees of freedom. All right? Okay, how about this one? Well, I have a joint here. Since I have a joint here, so definitely I have X, I have Y, I have rotation. But there's a special thing about this intermediate hinge that make the rotation from the left different from the right. Like, hey, you can rotate whatever you want, but I also can do whatever I want too. So this other part has extra rotation, so it adds more. So I have 1, 2, and then 3 and 4. If you substitute in the equation of the plane truss, how many joints? It's a 3 joints. 3 by 3 equal to 9 plus S equal to 1. So it's gonna give you 10. 10 minus the reactions, I have 6 reactions. So it's gonna give you 4, and this is the 4 degrees of freedom that I have. All right? Okay, so basically, when I have a degree of freedom problem, or I ask you to determine the degree of kinematic indeterminacy, I don't substitute in this equation. I basically look at the structure and try to count the degrees of freedom at each joint. It's a very easy process. Like here, for example, this joint has 0 degree of freedom, but this joint has 2 degree of freedom. Has 1 degree of freedom, which is the translation. All right, let's talk about the guided support, because maybe you guys haven't seen. Have you guys seen this support before, back in the years?
No.
In any course? Okay, let's talk about it. All right, we all know this support, right? We know this roller, right? This is a support that only restrains the vertical movement, and it only have reaction like this. When you restrain a movement, there is a reaction. You restrain the vertical movement, so there's a vertical reaction. If you restrain the horizontal movement with the vertical, so there is 2 reactions. When you restrain the rotation as well, so there are 3 reactions. This is called roller, this is called pin or hinge, this is called fixation. This one is called guided support. So for the guided support, it's kind of like a mix between these two. It's like the fixed, like something like this. This one restrain the vertical so it doesn't move up, and it also has a moment. It's like fixed, but it allow the translation in that way. If I put it something like this, so that's allowed the vertical movement that way. So the reactions, this is reactions. Let's say Ry, and this is the moment. The reactions here, this is here, and there's a moment here, but it allowed the movement that way. All right. So for this one, I only have 1 movement, right? How about this one? I have also 1, but it's in a different direction. So it is in the direction of the roller that you have here. Since it's going up, allow the vertical movement. But the guided support always has moment reaction. Always has a moment reaction. How about this one? This is a cantilever. 3, so I have 1, 2, and 3. How about this one? This one has a moment because that's a hinge, and this one has a moment because this is hinge. This is, yeah, well, this is a free joint because the fixed, if I put something like this here, that's fixed. But this is a free joint in the space that can move. X can move, Y can also have moment. This one also can move X, can move Y, and also has a moment. This is also a joint that has X, Y, and can have a moment left different from the moment right. So it has translation and 2 rotation. So I have 1, 4, 8, 11, and 12. 12 degrees of freedom. If you want to make sure, try to count the number of joints and the number of S and the number of reactions, and substitute in this equation. Try to find them if they are 12 or not. Let's do it. 1, 2, 3. Oh, 1, 2, 3, 4, 5. So I have 5, 3 by 5. Plus S is equal to 1. Minus the reactions, I have 4. So I have 15 plus 1, 16. 16 minus 4 is going to give me 12. So I'm right. Okay? So you can basically draw them right away without even calculation. But if I ask you in the exam, try to find out, you have to write the equation, you have to substitute in the equation, get a number, and show me the degrees of freedom on the figure. All right, so let's do this one. this one has a rotation, and this one has also rotation and translation. Okay, how about this one? How many degrees of freedom in this complex structure that has lots of fixation? 3. You only have one free joint here that has X, Y, and rotation. All the other joints are restrained by a fixed support. How about this one? These are the free joints, so I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's the only free joints that are that can move 2 translation and 1 rotation. Yes.
Is that a hinge? So on
Which
the,
one?
On the complex one that you had on the.
This one?
Yeah. Is that a
All
hinge?
these are fixed.
But the one in the middle that's also fixed.
No, it's
This
just a
here,
joint.
that's a free point.
Okay.
That's like multiple members are like coming at one joint. I just put a single point on them. All right, it's something like these, like this one. Like these are free joints. If I have fixed, I have to have something like this, a line with a dash line that means that this is a soil underneath this thing. Okay, so for this one, I have a free joint here, so I have 3, 3, 3. So I have 9 and 9, 18 degree of freedom. By the way, this is actually represent a building, a multi-story building like the building that we are in. But this is a 2D structure. So it only has 3 degree of freedom because it cannot move out of the plane. But if this is a 3D structure, how many degrees of freedom at each one of these points? 6, because it's gonna have 3 translation and 3 rotation. Like a structure like the one that we are in right now, this corner has 6 degrees of freedom, and the top corner has 6 degrees of freedom. Because every corner can move X, can move Y, can move Z, and can rotate about X, rotate about Y, and rotate about Z. Okay, so let's solve an example that can be in the midterm or can be in the quiz and see how it looks like. All right, can you guys look at the camera? I'm gonna use this part of the board. All right, example. All right, this structure is gonna be a little bit tricky. I'm gonna have fixed here, and I'm gonna have hinged here, all right? And I'm gonna add a bracing in this structure. Do you guys know what bracing is? So when you have a structure and you wanna to restrain the lateral movement, you add like a cross. So if it wanna move that way, this member can catch it. If you wanna move the other way, this member can catch it. But the question that you should ask me, how about this point? Is these 2 members are connected together or they are separate? Like when we pour the concrete or when we make the steel, are they attached or they are just free? Well, let's consider them they are connected together. Okay, if they are connected together, we have to consider this as a joint. The thing is that might make you confused, this intermediate hinge. Like, is this a member? Is that like a little member or, so what's going on here? So just for clarification, if the 3 members are connected to the intermediate hinge, they are gonna be like this, but this is not the case. The case is, this frame is on its own. But the thing is, I wanna put this here as a link member to support this frame. So the way that we do it, we either draw it that way, but the thing is if you see it that way, you will see, oh, that's a free, it's not connected to the structure. So we put like a little line to tell you that this link member is connected to the structure. So basically, this is not a member. This is just like an indication that the link member is connected to the structure. So basically, all this is one joint. But this is how we draw it or how we make it in a structure analysis problem. This is how we say this is the model of the real life. Okay, you guys got that? So this little thing is not a link member. Sometimes also in your homework, you will find something like this and you will tell me, oh, is this intermediate hinge on top of this? There's no way, like, I mean, it's kind of like to represent that this is a joint. Some textbooks make it like a circle like this. So this is equivalent to this, all right? Also equivalent to this. Every textbook is different in the way they make the problem. All right, so I give you this problem. I also add a little bit of complexity, and I add a spring here. And look at the question. This is how the question is going to come in the exam. I will ask you, determine IS and show the redundance. And IK and show the degrees of freedom. This is how the question you're going to see. Determine IS and show the redundance, and determine IK and show the degrees of freedom. Okay? So let's see how we can solve this problem. First, this is how you write the solution. You will start, for example, by IS is equal. This is a frame. 3M plus reactions plus RS minus 3 joints plus S. You have to write the equation. You got 3 points. Then you have to substitute, but to do this, you have to count the number of members, the number of joints, the number of reactions, the number of S, the number of RS. So I have the members 1, and since I count this as a joint, so every one of these is going to be a member. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 members. Joints 1, 2, 3. This is all one joint, so this is going to be 4. This is a joint 5, and this is joint 6. So members 1, 2, 3, 4, 5, 6, 7, 8. Joint is 1, 2, 3, 4, 5, and 6. All right. So this is a joint, and this is a joint, and this is one single joint. Does anybody have any question on this? We talked about this, and we said this is all a joint, not like 1, 2, 3, 4. So not too many. Just like a way to represent the structure. Okay. How about the reactions? How many reactions do I have?
5.
5. I have 3 here and I have 2 here. Excellent. How about S?
Also
The number.
5.
The S is the number of conditional equations. Okay, let's count them. Okay. By the way, this is a hinge, not intermediate hinge. This is different than these ones. So this hinge, we already calculated that there is reactions here. It might look like intermediate hinge. Intermediate hinge is something intermediate, not a support. Okay. So let's count them. This one is going to give me how many equations? 1. How about this one? 1. Why not 2?
Because
It's not about the number of members, it's the number of structures connected. This one is going to give you 2, but this one is going to give you 1 because this is a structure and this is a structure. 2 structures connected together. This one has 1, 2, and 3 members connected to it. So 3 minus 1 is going to give you 2. This 2 minus 1 is going to give you 1. All right, so excellent. So I have 2 here, 1 here, and 2 here. So this gives me 5.
No. 1, 1, 1.
Oh, sorry. 1. Okay, so this is 1, 1 is gonna give you 3. RS, how many springs?
1.
1. I only have 1 spring, 1 rotational spring over there. Okay, let's calculate. 3M, so 3 by 8 plus reactions, 5 plus RS equal to 1. Minus 3 joints, 3 by 6. And S is equal to 3, not 5. Okay. So 24, 29, 30. So I have 30. Minus 18 plus 3 is 21. So I have 9 redundant 4s. The structure doesn't need to be determinant and stable. We are going to find if they are internally or externally. But let me ask you a question. What do you think? Do we have any internal indeterminates here in the structure?
Yes.
We do. The numbers we're going to find out how many we have because it's a little bit tricky. If this is not intermediate hinge, I would directly say I would cut here and cut here and cut here and make it open structure. But since I have intermediate hinge here, if I cut in this one, what is going to happen? This part is gonna be unstable. It's gonna be something like this. We cannot cut in a structure and make it unstable. So I'm gonna hold into that for a little bit. We calculated this equal to 9. Well, let's actually show the redundance right now. So I'm gonna draw the structure. That's why you're gonna do in the exam. You're gonna take the same structure, draw it again. You have to draw the structure again. And then, all right, let's see how we can make this structure stable and determinate. First, I would say, the thing is, let's say I'm gonna cut here, okay? That's not right, but you're gonna tell me why it's not right. I'm gonna cut here, okay? And cut here, and cut here. What do you think about this?
There's
No.
none where it is done.
So if I cut here, this is gonna give me 3, and this is gonna give me 3. If I cut in the intermediate hinge, how many I will get? 2, right? Because the thing is, the intermediate hinge, when you cut in the intermediate, there is only 2 internal forces. Okay, so this is not intermediate hinge, this is fixed. When you cut in any structural member, you will find 3 internal forces: normal, shear, and moment. Intermediate hinge, make it a little bit special. Makes the moment equal to 0. So when you cut, there is only normal and shear.
Yeah.
So there's 2 internal, this is 3, 3. So I have right now 3 and 3, 6, and 2, 8. So I got 8 out of this one. And then, so we have,
But that's stable?
that's unstable.
Oh.
But why it's unstable?
Because there's a hinge?
This one is gonna make it a swinging. Like once you cut this here, this one cannot hold it. That's why I said it's not right.
Oh.
However, the numbers are right. 8 is right. But this is unstable. So let's find a stable solution. Can you tell me?
Well, you can cut the bottom too.
So the thing is, to make this stable, you have to cut and open all these vents and make one holding them. So I need one of these that doesn't have intermediate hinges to hold them. So I either leave this or leave that. So let's say I'm gonna leave this, but I'm gonna cut here, and I'm gonna cut here, and I'm gonna cut here. So this vent right now is
So-
open, and this vent right now is open, and this vent right now is open. So the whole structure is open right now, and is holding on this one fixed member. Yes.
The one at the bottom right, is that one not connected to
Oh.
the hinge?
You are right. That's totally right. So this one actually cannot work. So we need. I didn't see that one. Good job. So basically, I can't cut in this one.
The other left bottom.
But when you make the hinge
Oh.
a roller,
Okay. Let's see that.
or you open
That's
one
a
of the
trick.
sides.
Okay. So if I open this one and I open this one, and actually you have to open, when you open this one, you have to open it from here. Like this, at the intermediate hinge, not in the middle. So this one is gonna give you 2 here, and 2 here, and 2 here. That's the only way that you can get this structure. By the way, sometimes it gets a little tricky.
Can
But I'm
you
not gonna
open-
give it to you that much difficult.
Can you open the sides?
Hmm?
Can you open one of the sides?
Which one? Like these ones?
Yeah.
Well, there's multiple options, but every option you have to analyze. Like the way that we have done it, like I have done it wrong, and then somebody, oh hey, this one is gonna be like swinging, like so that one, this one is right now. Like this one, if I open this one and open this one, so this is gonna give me 2.
2, 4, 6.
Let's say 2, and this is 2, and this is 2. All right. So this one right now is right. So I got 6 out of the 9. All right. You said, what if I cut what?
Instead of the hinge, or you were gonna cut the side.
Like here?
Yeah.
You can cut from here if you want. And make this one open. And then you are gonna cut from this one, and you can cut this one.
So it's
So
2,
the whole
4,
thing
6, 7, and
Is
then
open. But I need to make sure that this part is still like, okay, let's actually do it and try it if it's gonna
it
work.
is not.
It's not gonna work?
No, because you
let's
have the
see.
hinge at the bottom. So you can, but you can cut the one to the.
On the right.
But the hinge in the bottom is annoying.
Alright, let's put it here. And we have spring here. By the way, the spring here, make this connection like this. You can deal with this connection at just one connection. Okay, it's just a semi-rigid connection, so both are the same. Okay, you're saying, what if I cut here? If I cut here, this member is a stable. And if I open this vent, this is still stable. And if I open this vent, this is gonna be still stable. And if I open
No.
this vent like
Oh.
here, okay, let's see. All right, so this part is stable. Why? Because it's still holding on one fix. This part is stable because it's holding on one fix, but this part,
Not stable.
look, this part of the structure is unstable because the whole thing is on a hinge, so it can flip, so it's gonna make it unstable. So for now, I see this one, this, and that is the
That's
our,
246.
that's 6. Let's find what we can do. By the way, with this, I can actually take this whole thing. This whole thing, you don't need the 2 reactions at the support.
So that's 2 more.
So that gives you this one and this one. I want to just look, make sure that we have the number of members right. 1, 2, 3, 4, 5, 6, 7, 8. Joint 1, 2, 3, 4, 5,
6.
6. So we have these 6 reactions is 3, and this you have 2. So you have this 5 is giving you 1, 1 and 1, 3. Rotational spring 1. So 3, 4, 13, 16, 18, 21. Okay. So let's see. Right now you have this one has 2 redundant, like 2, and then it's gonna make it 4, 6, 7, 8. So we need to find another one that the structure.
Can you do anything with the spring?
No, because then it's not gonna
It's
be
not
rigid.
stable, right?
Oh. I have this and this problem as a ruler in this example. Not hinge, but let's see. Well, if we solve it, so give me IS here is 8, not 9. But we were supposed to be. So the thing is, if we remove this rotational spring, and this is going to be supported on a hinge, and this one is going to be unstable. And if we make this hinge, so
Teacher,
I'm trying to find what is missing here.
teacher,
Hmm.
isn't the hinge in the bottom right corner giving us one extra formula because it's connecting to structures?
Which one?
The one
This
at the
one?
bottom right, yeah, because it's connecting to structures technically.
Oh, that's right. Well, you are right. So, well, the thing is, what you're right about, if my structure is something like this, I would say that what we did is right. So, since we have it, good job. Since we have this one is here, that also gives you that the moment here is also equal to 0 at this structure. Not only one member that gives you the moment is equal to 0, but this one also gives you that the moment is equal to 0. Mine is roller, so we didn't have, but it still actually have the same issue. By the way, this one is so wrong, even with its ruler. So I'm gonna fix it and put it down there because I still cut here in the middle. I shouldn't done that. I still have to cut here, not here. So the S here, this one is gonna add an extra equation because you have two members are coming to this one, and S is gonna be equal to 4, and this one is gonna be equal to 4, and this one is gonna be equal to 8. Good job. So I have this one is 4, and this one is 4, and this one is 8. So that means this one is right. You cannot like remove the rotational spring. You can remove the rotational spring, but you have to keep some supporting here, at least roller. So you have 6. Internal and 2 external.
So the hinge at the bottom does affect the.
Well, the hinge does affect this as a support, like
No,
this
but I
one.
mean affects the.
But you
S.
cannot count it double time because that also make the moment for this one is 0 too, because there's an because this one is kind of like this is how it's supposed to be. I should have when I drew this because this is like kind of link member. I should have drawn it something. Let me see if I did it here that way. I didn't, but if I want to do it, if I want to do this one, I would do it that way. Something like this. And that's make it as a link member. And you would count this as a 1. But the way that I did it, I merged it with this hinge.
Okay, so just to make sure that I understand.
Yeah.
So basically, the support on the right side is a hinge. What is
This is a hinge, yeah.
It's connected right to a link member, so that's why it's 4.
This is a link member, and this is a hinge.
Okay.
Alright? But the thing is, I merged this support from the link member because link members are something like this. Has one at the end and one at the end. So I merged it with the same hinge here. However, both are the same. Both is gonna give you the moment for this member is 0 and the moment for this member is 0. Usually, we don't count this as intermediate hinge because we counted reactions at this one. However, the moment is still calculated as equal to 0 at this one. It's a little bit tricky one, but it's good that we caught it, and I'm gonna fix it here. So we have 2 external here. So just for you not to be confused, I should have drawn this as something like that, and then you would count this as another S and give this extra 1, so it's gonna be 4 rather than 3. All right, so right now we finished the IS. Let's move to the IK, which I believe is much easier. What is the rule for IK? It's much simpler rule. 3 joints plus S minus reactions. So the joints are 6. 3 multiplied by 6 plus S, which is 4, minus the reactions, which are 5. Okay, 3 multiplied by 6, 18, so we have 22, minus 5 is gonna give us 17. All right, next is that you have to draw the whole structure again. Let me put this as a hinge, and then you have this as a link member. And then, by the way, this is not a link member. Do you guys know why? This is a link member. This is not a link member because it's fixed here. It's a frame member. If I put that circle down here, like these circles, it become a link member, has moment equals 0 at the end and moment equals 0 at the other side. So I'm gonna put this here, and this is attached to the fixed, and then I have the spring. All right, let's count the number of degrees of freedom. Do I have degrees of freedom here?
No.
Okay, so how about here? I have X, 1, 2, 3, and what else? 4 coming from this member, because this member, its degrees of freedom is different from the other structure. How about this one?
But doesn't that intermediate hinge have 4 on its own?
I told you this is only one joint. So since it's one joint, it's something like this. Same thing like this one. Here you have 1, 2, and 3, like 3 here, and this one has a 3 here. It's something like this one. So this joint actually are attached together. So when you have this one, if you said that this is have another 3, that means that this point can move x, y, and z differently, and this one can move x, y, and z differently. So that means this doesn't provide any attachment to this. So the main idea from this link member is to prevent the horizontal or the vertical movement of this joint, but allow it to rotate freely. Okay? So basically, the only degrees of freedom that this one add is another translation here.
Like, why don't we add like another like counteracting moment on that thing member?
I don't understand that question. You are talking about this one?
No, I'm not talking about the joint. I'm talking about the intermediate hinge.
This one?
Not the other ones from the diagonal.
This?
No, top left. Yeah.
Yeah.
Shouldn't there be like another moment?
Yeah, it's one here and one here.
Because those 3 act as one thing.
Oh, okay.
So these 3.
It's as if those 3 were one.
Yeah. What I'm doing here is just a representation to see like there's an intermediate hinge here. But at the end of the day, in the real life, they are one joint and they are move x and y together. But the only thing this member can make something like this, can rotate.
Alright.
Okay. So x and y translation for all of them are the same, but rotation, this can rotate and this can rotate differently. So you have one and another one here. So all right. Same thing here. You have 1, 2, and this member have 3 and 4. But let's count from 4. So I'm gonna count 5, 6, 7. All right. So this is gonna be 5, 6, 7, 8. This one, the same like this one. So I'm gonna have 9, 10, and this is gonna be 11 and 12. How many left do I have? We said 17, so I still have 5 left. Let's find them. Definitely this has 3. So I have 1, 2, and 3. So I'm gonna count from 12. I'm gonna have 13, 14, and 15. This one cannot move x, cannot move y. This one is gonna only add 2. This member is gonna be, by the way, x and y are restrained. Like this point cannot move. You will tell me, oh, this is a joint. Let me add x and y and rotation. However, this point is attached down like this one, something like this. Want to move x and y, so x and y need to be canceled. So let's actually put the whole 4. So the whole 4, you will tell me, okay, I'm going to add 1 here and 1 here, and this one is going to rotate, and this one is going to rotate. I'll tell you no. This joint, yeah, want to move x and y. However, this is restraining this joint, so this is going to be canceled. These 2, x and y. This one cannot move because this one is blocking them. You'll tell me, but this is a little bit away. No, it's not away. It is just attached to this joint. So this joint can move freely from this joint, so you are having another 2, which is counting from 16 and 17. So this is added the 2 degrees of freedom that you have here. This is, I believe, one of the most difficult settings that has everything related to redundance and also the degrees of freedom. Because we have springs, we have multiple intermediate hinges, we have closed vents, we have everything in this problem. Okay? So if you understand this problem correctly, I believe you will solve any problem. So to get the full points in the exam on this problem, you have to write the equation, you have to find the final answer, substitute in the numbers that you have here, write this one, and write this one. Write this equation, substitute, and show the degrees of freedom on the diagram. Okay. Let me do a grid example to close this stuff. Yeah.
The quiz is going to be next week, Tuesday or Thursday?
Let's make it Thursday.
Okay.
Right? Thursday's fine?
Yeah.
Yeah.
Cool. Okay, let's switch the camera to this part. Alright, so the grid also is difficult because it has two moments, so I also need your focus. So I'm giving you a grid like this that is fixed here. And find the degree of kinematic. Find the degree of kinematic and static indeterminacy and show redundance and degrees of freedom. Same thing, but I have to tell you something about these supports. You will, if I didn't, you have to ask me, is these supports spherical or cylindrical?
Right.
So I'm telling you, assume spherical supports. Okay, let's do this.
So that hinge right there that you're showing us is similar to those intermediate. So it's not three.
No, not cylindrical.
No, I mean the little the
This
one.
one?
Yeah. So it's not three members connected to it. It's two structures.
Yeah. Okay, so let me make it much clearer. So it's gonna be, this one is one member, like this, and this one
Perfect.
is something
Okay.
like this.
Yep, makes sense.
Right? Okay. Alright, so let's solve this part. So I have IS is equal to 3 members plus reactions plus rotational springs minus 3 joints plus S. I have to count the number of members. How many members do I have here?
1, 2, 3.
1, 2, 3, 4. Because
No.
this is still a joint. This is still dividing this as a joint. Like when we have this, once you have this in between members, or even something like this is still
Okay.
a joint. But this is a little bit tricky because it's a 2D. But anyway, if you are gonna count this as a joint, these are 2 members. Like if you are gonna say that I have a joint
Okay,
here,
okay.
so it's gonna divide this as a 2
Right,
members.
right.
Alright, so I have joints 1, 2, 3, and 4. So this is gonna be 4. And I have reactions. Okay, how many
5.
reactions do I have here? I said this is a spherical. How many reaction I have here? 1, which is the Y reaction. Here, 3, and here's 3. So I have 3 and 3, 6, and this one is gonna be 7.
No,
All right.
Professor. Sorry, the joints. Can you show me the joints again?
Okay, I have a joint. Oh, I put
5,
4.
right?
Oh yeah, so 1, 2, 3, 4, 5.
Perfect.
And S is the tricky one. Okay, so what is the rule for S? It's either one of 2 things. It's either n minus 1 or 2 multiplied n minus 1. This is F cylindrical and this is F spherical. And why is that? Okay, let's do it with this rule because I told you it's a spherical hinge. So S is gonna be 2 multiplied. How many structures are connected at this hinge? 3 or 2? 2. So I have 2 minus 1 is gonna give you 1, so you have 2. Well, tell me, but you told me that this is a structure and this structure give you 1 extra equation. Yeah, if it's a frame, it gives you that the moment here is equal to 0, but this one is a spherical, so it has 2 moments. Has the moment around this is equal to 0. Like imagine that this is resting on this, so bending moment is equal to 0, and the summation of the torsion is equal to 0. So there's 2 equations we have here. So S is equal to 2. Alright, so let's substitute here 3 members.
Where you get the cellular reactions?
Yeah, right?
Alright, I have 3 here, 2 moments and one vertical, 2 moments and 1 vertical, 6, and this one only 1 vertical, it gives you 7.
Because this is first.
Because this is a circle. So circle only give you 1 reaction that way. If it's cylindrical, like this, it gives you 1 that way, and it gives you, it resists the torsion, like 1 that way. Alright? Okay, so I have 3 members, 3 multiplied by 4, and reaction 7, there's no springs, minus 3 multiplied by the joints 5, plus S2, okay, let's find out. 3, 4, 12, 19, minus 17 is equal to 2. Can we find these 2? Where's this? And I'm gonna draw. Alright, can you guys tell me how can I make this structure determinate and stable, or how can I show the 2 redundants? Okay, there's one that is really easy. If I remove this part, is this a structure is gonna still be stable? It's gonna be stable, right? Because the thing is, even if I remove this structure, this fixation can hold the same thing. So definitely this one I can remove, but I can do it here, so I have to do the structure again. I'm gonna do it something like this. And the verse redundant is this vertical reaction. Do we have anything internal? Nothing internal, right? Everything is open. This is open structure. Okay, that's reaction number 1, or redundant number 1. Let's call it R1. How about R2? What should I do?
Could you remove the fix?
I can remove the fix and put what? If you remove the fix, this is gonna be, the whole thing is gonna be like this. It's gonna be like a swing.
Ah, okay.
Alright? Because this one is not fixed. If this one is fixed connection, so I can remove it. Like
You
if
can put a
this,
restrictive roller thing.
if this one
guided
coming to
support.
this, I would remove the fix, but this is not the case.
You can put a guided support.
There is no guidance in the grid system. However, you can make cylindrical support. Okay? Because you are gonna put this cylindrical, like you can make it something like this, and you release the torsional moment.
Alright.
And this one is gonna be okay. That's a one solution. So this is gonna be redundant. By the way, torsional is always in the direction of the member, like something like this, because that means that this member has a torsional like this. The bending moment, I would draw it out of the plane, because the bending moment is something like this, so it's out of the plane. So these are the 2 redundants. Redundant number 2. By the way, there's another solution. If you cut here, how many reactions are gonna show up?
2.
By the way, this is spherical, not cylindrical. Okay. So, this is not this is. By the way, this is a stable and this is a stable indeterminate, so, right? These 2 structures are stable and indeterminate. The only, okay, here's the redundant number 1 still. The thing is, this structure is resting on this structure, something like this. So the only thing that this support is providing on this support is that one is resting and giving Y reaction to the other one. So if you cut, you are gonna show this. This is R2 and R2. So basically, if you cut here, you are showing the cylindrical support. So the cylindrical support, once you cut into it, you only show one internal force, which is the vertical reaction. If this is cylindrical, once you open it, you're gonna show 2 forces. Shear, which is
because
the
this
vertical,
is
and
spherical.
moment.
This is spherical, it's gonna be on
Spherical is only this one already allows the moment and allows the torsion. It only restrains the vertical movement. Like once you have this on that, that means, okay, you can move that way as you like, and you can translate that way as you like. And also, you can have a moment as you like, and rotate as you like, okay? But we either go up together and goes down together. So it's only the vertical translation. So this is also one way to solve it because it's only the vertical reaction. So this is right, and this is right. Okay,
You
so
can't keep the spherical support and remove the fix because of the rotation.
okay, let's say if I remove the fix. So I'm right now removing three things.
Correct.
This one is spherical, can rotate, and also it's gonna be unstable.
Why?
The thing is, I'll tell you why. Okay, let's put it that way. I'm gonna make this a structure. It's a good question. All right, and this is something, I'm gonna put it like this. All right, let's say I put a torsional load on this beam. I put a torsional load on this beam. Something
Yeah.
like this. Is there anything that this beam is gonna resist this torsional load? No. This
But-
basically, if you put load, this is gonna keep moving, and that's unstable. You will kind of like, oh, but it didn't fail. No, rotation. If the beam is, the thing is, we have supports to restrain the movement. I don't want this like somebody is making something with his leg, and the beam is keep rotating. That's a mechanism, not a structural system. So because this one only restrain the vertical movement, but doesn't restrain the rotation. Okay.
Got it.
All right. Okay, so how about the IK? And by the way, if you remove this, it's gonna give you 3 redundants, and we only have 2. So you only need to you can release something here, but not everything. So maybe I can release like the same way that we did it here. We did 1.
You can
If you wanna keep this one, you have to keep another one here. Like you can keep this, and maybe remove the, and make it cylindrical.
Does that hinge, the one that comes down, also resist? Like,
This
does
one?
that keep up the beam?
Which one? This
That
one?
yeah. Does it keep up the beam, or
This
is it
one,
just
it's
sitting?
either, this one, it's either that this beam is resting on this beam, or this beam is resting on this
Got
beam.
it. Okay.
And only resting, not doing anything else.
Got it.
If you have a grid like this, that are resting on a spherical and cylindrical support, that's still stable.
Yeah, because it.
Because this one, if you put torsion, this one is gonna resist it. If you put vertical, there's 2 reactions. If you put bending moment, they are gonna still, it's like hinged and roller, something like this. Okay, let's put,
So both of them will be external.
yeah, this is all this external. Because this is kind of, is not internal, it's kind of like, this one is providing a support for this one. Okay, so let's put IK. IK is equal to 3 multiplied by the joint plus S minus the reactions. So 3 joints is 3 by 5. No S, I have S is equal to 2 plus 2. Minus reactions is 7, so I have 15. So I have 10 degrees of freedom. Can we? Okay, let's locate the 10 degrees of freedom. It's a little bit tricky here, but I believe we can do it. All right, how many degrees of freedom do I have here?
3.
And who are these 3? How many translation, how many rotation?
2 rotation and 1 translation.
Excellent. So the translation, this one can go up. That's number 1. The 2 rotation is this joint actually can rotate that way, like this, and can rotate also the other way, which is like this. Do you guys can imagine the rotations? So it's something like this. So basically, this can move up and down, and can rotate that way, and can rotate that way, and that way. So that's how we represent them. So let me remove this. I hope that you guys can do the right hand rule or can imagine it without. So when I put 2 arrows, that means rotation. Okay, so that's 1, 2, and 3. All right, how about this one? How many do I have here? That's a spherical hinge.
1.
2.
If it's cylindrical, I'm gonna have 1. But if it's spherical, I'm gonna have 2, because the spherical is only, like, let's put it as a ball here. So it restrained the vertical, but I have torsional and moment are allowed. So basically this can bend and can rotate. So that's 5. Where's the other 5? Oh, there was a question here. Do you have a question? Let's answer it.
Yeah. No. The joints where the fixation is like.
This one's 0 and this one's 0.
Yeah, but like on the same line of action. Why?
This one?
No, on the top right. Yeah. Why don't we have the like the 3 and 2 pointing directly to the joint?
What do you mean directly to the joint?
So you see like how the forces are going like away instead of going like.
Well, I'm
That
just
doesn't
showing.
really-
You mean like, why did I make them outside the joint?
Yeah.
Well, you can make them inside the joint if you want. I just want to show that there's a rotation.
Okay.
Okay. All right. So this one is
Has
the
2 now?
this one. Actually, if we want to talk reasonable, we have 10. We're already done 5, so definitely there's 5 here. But let's find out where are these 5. Because this one has 0 and this one has 0, and we are done with this one and now where's this one? How this end up having 5? Well, if this is counted as a joint, that gives us 3, right? Gives us 1 translation and 2 rotation. However, we said that this one is going to give a Kessler-2 equation, but let's find them out. First, this can, let's focus on this member. This member can move up. And by the way, this vertical rotation connected the two together because both they have moved up together and down together. So this one applies for this and this. So they both have the same vertical movement. So that's 1. However, this member can have a separate torsion and a separate moment. And this member can have a separate torsion and a separate moment. So you have here 6, 7, 8, 9, and 10. This one has moment and torsion, and this one has moment and torsion, and they both can do it separately. Like this one can bend, can rotate, and this one can bend and can rotate separately. So, but they both have to move up and down together. Okay? All right, so I believe we covered. Let's solve another one question on the grid so that we can close this topic. And next time we're going to start with the analysis of arcs and cables. All right. Okay, let's put it that way. Wow. Same like the other grid system, and I'm asking you to find the IS and IK for this one.
Are those connected?
All these are connected. This is a joint, this is a joint, this is like the floor system that we are in right now. There's a column here, column there, and all these are beams that are intersecting together. Usually, actually, we call this system Banal beams. Have you guys heard about Banal beams? So, Banal beams is like if we have a huge span and like an open space that we don't want any columns in between, we make a lot of beams parallel to each other and intersecting with each other and connecting the whole system together, like this one. So that Banal beam actually can let us have a space of like 30 foot or 40 foot without any columns in between. We usually use it like for lecture halls and stuff like this. Anyway, So this panel beam system or this grid system, we need to find out what is the IS and IK, and we need to show the redundance and the degrees of freedom. Okay, how about the number of members, joints, reactions, and S? Okay, S and RS are equal to 0. Members, 1, 2. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 members. How many joints?
12.
1, 2, 3, 4. Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Reactions. 3,
3,
6, 9, 12, 15, 24. So I have 1, 2, 3, 4, 5, 6, 7, 8, 8 by 3 equal to 24 reaction. Alright, so let's find the IS. IS 3M plus R minus 3J plus S. So 3 members, 3 by 12, reactions
12.
24,
24.
and J is
3 times 12.
3 times 12. Okay, so I have 36 plus 24 is gonna give us 60, and 3 by 12, so this is gonna give us 24. So let's find out, where are these 24? Okay, let's find them. Actually, this is very easy. The thing is, you only need one fixation to make this whole system stable. Like, I would remove this, 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 and this one, and this one, and this one, and I made that, and this one too. So how many did I remove? So this one have
21.
sorry, this is a grid, so I only have one vertical, and you need to do this for every one. How many did I wrote? 1, 2, 3, 4, 5, 6, 7. 7 by 3, 21. So I still have another 3. Do you know where they are?
You open
They
one.
are internally in this vent. So I have to open one of these vents, and then once you open it, you're gonna find shear and torsion and moment. So that's the 24. You have to number them 1, 2, 3 until you come to number 24. So that's easy. I believe it's much easier than the other one. Let's find, even the IK is much more easier. Like if I put the IK, 3 joints plus S minus the reactions, the joints are 12. There's no S, reactions are 24. So I'm gonna have 12 degrees of freedom. Okay, let me draw this structure again here. By the way, you have to draw everyone separately, so I'm gonna make this.
3 at every joint.
Yeah, 4.
Where are the degrees of freedom?
The intersections.
The degrees of freedom at these joints. Excellent. So I have 1, 2, 3. 1, 2, 3. You have to count them 1, 2, up to 20. Sorry, 12. This is 12. That's it. And then the problem is solved. So with this, I believe we've finished the whole static, determinant, and indeterminate structure. We have solved many examples on beams, frames, trusses, and I believe we covered almost everything. So I believe you are ready for the homework. You are ready for the quiz. And definitely there's a question in midterm 1 on this part, like at least 25 points or something. So, I mean, like in midterm 1, we didn't decide yet, but next time we're gonna start a new topic. We are gonna start something called the analysis of arcs and cables. Okay? All right, see you guys next time.
Thank you.